Explain each of the following engineering terms. A. Hardness. B. Proof stress. C. Ultimate tensile strength, UTS. D. Young's modulus. C. Yield stress. A. Hardness. Hardness quantifies a material's resistance to indentation or scratching. It indicates how easily the surface of the material can be permanently deformed by an external force. Common hardness tests include Brinell, Rockwell, and Vickers. Higher hardness values indicate a more resistant material. B. Proof stress. Proof stress, also known as yield strength in some contexts, is the stress level at which a material begins to deform plastically, permanently. This means that at once this stress exceeds the proof stress, the material will not return to its original shape after the stress is removed. It defines the practical limit of elastic behavior for a material. C. Ultimate tensile strength, UTS. UTS is the maximum stress a material can withstand before fracturing or breaking under tension, pulling force. It represents the strongest point the material can reach before ultimate failure. UTS is typically a higher value than yield stress, as it measures the breaking point rather than the point of permanent deformation. D. Young's modulus. Young's modulus, also known as elastic modulus, describes the stiffness of a material. It quantifies the relationship between stress and strain within the elastic range, which is the region where deformation is temporary. A higher Young's modulus indicates a stiffer material that requires more force to deform a given amount. E. Yield stress, as mentioned earlier, can be used interchangeably with proof stress in some contexts. It refers to the stress level at which plastic deformation begins. However, depending on the material and testing method, there might be slight variations in how these terms are defined and measured. So, to summarize, hardness is the resistance to indentation and scratching. The units are measured in newtons per millimetre squared, and the importance is surface wear resistance and machining properties. Proof stress, yield strength, is the stress at the onset of permanent deformation in megapascals. Its importance is the structural integrity under load and design limits. Ultimate tensile strength, UTS, is the maximum stress before breaking. The units are megapascals, and its importance is for material strength and safety margins. Young's modulus concerns the stiffness of the material. It's in gigapascals, and it's important for deformation under load and vibration response. With reference to stresses within engineering materials. A. Explain each of the following terms. 1. Tensile stress. 2. Shear stress. 3. Compressive stress. B. List 2 components within a diesel engine that are subject to the effects of each of the 3 stresses listed in Part A. C. State the component in a 4-stroke diesel engine that has a maximum recommended service life due to constant cyclic stress. A. Explaining different types of stresses. 1. Tensile stress. Definition: a pulling force that acts to elongate a material, stretching it in the direction of the force. Imagine pulling a rope to extend it. Shear stress. Definition: a force that tends to slide or deform one part of a material relative to another along a parallel plane. Imagine sliding two bricks against each other, causing them to deform and potentially be damaged. Compressive stress. Definition: a pushing force that squeezes or compresses a material, shortening its length in the direction of the force. Imagine stacking heavy weights on top of a block, pushing it downwards and potentially crushing it. B. Components experiencing different stresses in a diesel engine. Tensile stress. The connecting rod. The pull of the piston on the connecting rod creates tensile strength throughout its lengths. Cylinder head bolts. The pressure generated during combustion pushes outwards on the cylinder head, requiring the bolts to resist this tensile force. Shear stress. Crankshaft bearings. The connecting rod rotates on the crankshaft bearing, creating frictional shear stress between the two surfaces. Gear teeth. When gears mesh, their teeth slide against each other, generating shear stress at the contact points. Compressive stress. Piston. The combustion pressure pushes down on the piston, creating compressive stress throughout its crown. Cylinder walls. The pressure inside the cylinder also pushes outward on the cylinder walls, subjecting them to compressive stress. C. The component with the maximum cyclic stress in a 4-stroke diesel engine. The component in a 4-stroke diesel engine with a maximum recommended service life due to constant cyclic stress is the piston and its rings. These components experience repeated cycles of high pressure during combustion, followed by release of pressure during exhaust and intake strokes. This constant cycling, along with high temperatures and friction, contributes to wear and tear, necessitating a recommended service life for their replacement. A. Explain each of the following terms. 1. Plasticity. 2. Shear stress. 3. Young's modulus. 4. Safety coefficient, factor of safety. B. State 2 factors that may influence the safety coefficient in operation. A. Definitions. 1. Plasticity. The property of a material to undergo permanent deformation under stress. Unlike elastic materials that return to their original shape after stress is removed, plastic materials retain a portion of the deformation. Imagine bending a paperclip. It retains the bend after you let go. 2. Shear stress. The stress that tends to slide or distort one part of a material relative to another along a parallel plane. Picture sliding two books against each other, causing them to shear and potentially tear. 3. Young's modulus, also known as the elastic modulus. It measures the stiffness of a material. It quantifies the relationship between stress and strain within the elastic range, where deformation is temporary. A higher Young's modulus indicates a stiffer material that requires more force to deform a given amount. Think of a stiff beam compared to a limp noodle. 4. Safety coefficient, factor of safety. a factor applied to the design load of a component to ensure it has sufficient strength to handle actual operating conditions, with a buffer against unexpected stresses or material imperfections. It acts as a safeguard against component failure and associated risks. Imagine adding extra bricks to a bridge design to ensure it can safely support cars and trucks. B. Factors influencing safety coefficient. 1. Operating conditions. Unexpected loads or environmental factors like extreme temperatures, corrosive environments, or sudden shocks can necessitate a higher safety coefficient to account for these additional stresses. 2. Material properties. Variations in material properties due to manufacturing processes, aging, or inherent inconsistencies can require adjusting the safety coefficient to ensure reliable performance despite these uncertainties. 3. Explain each of the following terms. A. Ductile cast iron. B. Tensile stress. C. Work hardening. D. Shear stress. E. Young's modulus. A. Ductile cast iron. Ductile cast iron is a type of cast iron with improved ductility and toughness compared to traditional cast iron. This is achieved by adding a small amount of magnesium or cerium during the manufacturing process, which changes the graphite microstructure from flakes to spheroids. This results in a material that can deform considerably before breaking, unlike the brittle nature of traditional cast iron. Ductile cast iron is used in various applications like pipes, automotive components, and machine parts requiring strength and some flexibility. B. Tensile stress. Tensile stress is a pulling force acting on a material, trying to elongate it in the direction of the force. Imagine pulling a rope. The rope experiences tensile stress, stretching as you pull harder. It is one of the basic types of stress encountered in materials, alongside compressive stress, pushing, and shear stress, distortion. C. Work hardening. Work hardening, also known as strain hardening, is a phenomenon where a material's strength and hardness increase as it undergoes plastic deformation, permanent shape change, due to external forces. Imagine repeatedly bending a metal wire. It becomes progressively harder to bend further as the work hardens. This property is utilized in metalworking processes like cold forging and wire drawing. Shear stress. Shear stress is a force that acts to slide or distort one part of a material relative to another along a parallel plane. Picture pushing two bricks against each other. They experience shear stress at the contact point, potentially causing them to slide and deform. It is another fundamental type of stress along tensile and compressive stress, and it plays a crucial role in phenomena like friction and material failure. E. Young's modulus. Young's modulus, also known as the elastic modulus, measures the stiffness of a material within its elastic range where deformation is temporary. It quantifies the relationship between stress and strain within this region. A higher Young's modulus indicates a stiffer material that requires more force to deform a given amount. Think of a steel beam compared to a rubber band. The steel has a much higher Young's modulus, making it much stiffer. Explain each of the following engineering terms, stating one material that exhibits each property. A. Brittleness. B. Ductility. C. hardness. D, malleability. E, toughness. Here are some definitions of the terms and an example of a material that exhibits each property. Brittleness. A material that is brittle will break or crack easily under stress. An example of a brittle material is glass. Ductility. A ductile material can be drawn into thin wires. An example of a ductile material is copper. Hardness. A hard material is resistant to scratching or indentation. An example of a hard material is diamond. Malleability. A malleable product can be hammered or pressed into thin sheets. An example of a malleable material is gold. Toughness. A tough material is resistant to breaking under impact. An example of a tough material is rubber.